Yes, let me start introducing yourself.
My name is Avantika. I belong to Hisar, which is in Haryana, and I have completed my schooling from Hisar, and I have graduated and post-graduated from Guru Jumbeshwar University of Science and Technology, Hisar.
Yes, good. Yes, go through on board, whiteboard. Good.
Sir, is the back camera on Zoom meeting, or I have to?
Yes.
Is this visible, sir?
Yes, visible. Yes, I explain on valence bond theory.
Okay, sir. So valence bond theory was given by Pauling, and according to valence bond theory, there is covalent bonding between metal and ligands. It says that the metal has vacant orbital and ligand have filled orbital, and it is formed by the overlapping
Yes.
Sir, the VBT only involves the d orbitals of metal.
Yes. Yes, what's the difference between tetrahedral, octahedral, and square planar complex? Why VBT?
So, like, if in tetrahedral complexes, for according to VBT, there are two hybridization possible for tetrahedral complexes, that is sp3 and dsp2. sp3 is formed by the involving outer d orbitals, and dsp2 is formed by involving inner d orbitals. For example, if we take like if we have taken cobalt and ammonia 3 plus, then the hybridization and we can calculate as cobalt 3 plus. It is the atomic number of cobalt is 27, and it is 4s2 3d7 in its normal state. So after removing 3 electrons, the hybridization will be d6, and the d orbitals, because ammonia is a strong filled ligand, so it will do pairing.
Yes.
So the d orbitals will be filled. So here it is 3d orbital, in VBT we fill electrons according to, like, first we fill in n-1 d subshell, then ns subshell, then np subshell, np shells. So here two vacant d orbitals, and there is one vacant s orbitals, and three p orbitals are vacant. Then here there are 6 ammonia ligands which will donate electrons. So the ammonia will donate its electron pairs in these vacant orbitals.
Yes.
So
Yes,
it's
yes, carry on.
so its hybridization will be D2sp3 because it is involving inner d orbitals, and it is a octahedral complex because it has 6 coordination with 6 ammonia ligands. That is, it has 6 coordination number, and D2sp3 hybridization. And if but the one limitation of VBT is that it can't explain the structure of copper with 4 ammonia CuNH3 4 plus, because according to VBT, if we form the if we find the hybridization of CuNH3 4 plus according to VBT, then we can find that because copper has D9 configuration 4s2, then in 2 plus it will have D9, and if we fill the d orbitals, then we see that there are no vacant d orbital present. So according to VBT, its hybridization is sp3, but from experiments we have find that it has, and according to sp3 hybridization, it is it have tetrahedral geometry, but actually it doesn't have tetrahedral geometry. So the excite if we excite this one electron of d orbital to 4p orbital, then 4pz orbital, then accordingly it's now we have put this electron in 4pz orbital. Now this hybridization will come as dsp2, which is square planar, but this is also not the actual hybridization of CuNH3 4 plus. So from experiments we have found that it's it is not involving this inner d orbital. Its hybridization is sp2d.
Yes, good.
One limitation
Yes, yes.
of VBT is also that it can't explain the distortion in octahedral complexes, and it can't explain why the strong ligands do pairing and why weak ligands can't do pairing. The VBT also doesn't explain that why the observed or experimented magnetic moment comes different from the calculated magnetic moment.
Yes, good. Why tetrahedral is always high spin and square planar is always low spin and octahedral is high spin and low spin? Why? Explain.
So in tetrahedral
Yes, first
complexes,
remove. Yes, first these remove, then explain on board.
so can you repeat the question?
Why tetrahedral is always high spin and why square planar is always low spin? Why octahedral is two is high spin and low spin? Explain one by one.
In tetrahedral complexes,
Yes.
when we fill electrons, uh, like in tetrahedral complexes, mostly the hybridization is sp3. So the strong and weak field ligands doesn't impact it because like in s orbital, when the ligands approaches towards the metal ion, the s orbital is very close to the nucleus, and p orbital is and far, and d orbital is more far. When the ligands are approaching towards ligand field is approaching towards the orbitals, the s orbitals is not impacted, so the s orbital energy is not raised. So here no splitting and no excitation of s orbital occur. And when the ligands approaches the p orbitals, excitation of p orbitals occur. All the three p orbitals get excited to an upper energy levels because all the p orbitals are in axial plane, but in d orbitals there are 5 types of d orbitals: dx y, dy, z, dzx, and dx square minus y square and dz square, where dx square minus y square and dz square are axial orbitals, and dxy dxy and dyz dxz are non-axial orbitals. So when the ligands approaches towards the uh, in octahedral complexes, when the ligands approaches towards the d orbitals, Actually, the ligands are coming towards the center of the metal, because according to crystal field theory, the metal is present at the center, and when the ligands are approaching, so the ligands will approach in such a way that it will form octahedral complex. So ligands have to approach towards the faces so that it can form octahedral complex, because the ligands form the lattice and the metal is present in the void. So to make this octahedral void, ligands have to enter through the face centers. But while and entering through the face centers, ligands found that there are axial d orbitals present. So the axial d orbitals, ligands will approach towards these axial d orbitals, which is dx square minus y square and dz square, and that the energy of these two orbitals, dx square minus y square and dz square, will be raised, and dxy will is present at the edge center, so it will not get repelled more. So this the energy of these orbitals will not be raised, these energies will be decreased. So when we fill the electrons in d orbitals in octahedral complexes, if the spin is high, then we will if there is a strong field ligand, then we feel like this, because if so that Hund's rule of maximum multiplicity is followed. And if the ligand is strong, then we will first fill these under excited orbitals, and then we will fill the upper orbitals. And in
Yes.
Sure.
Yes. Next, move on. CFT. Yes. What the basic principle of CFT? Crystal field theories. Explain. What the main purpose of CFT in coordination chemistry? What the uses of CFT in coordination chemistry? Explain.
Sir, crystal field theory is a solid state physics theory. It assumes that the metal and ligand are point charges. According to CFT, metal is a stationary charge and ligand is a moving charge, and there is electrostatic attraction between these metal and ligand. So the metal and CFT assumes that there exists ionic bond between metal and ligand.
Yes, yes.
There exists ionic bond between metal and ligand. So the metal ligand approaches towards the metal, and the metal is present in void where the metal has a positive charge and ligand has negative charge. Here the ligand that is negatively charged, it forms a lattice, and the metal which is positively charged, it is present in the void of this lattice. There are different complexes formed in the way the ligands are approaching towards the metal and forming octahedral or tetrahedral complexes or cubic complexes. If we form cubic, if we are forming cubical, if we have to form cubical void, for example, then the ligand have to approach towards the metal through the corner atoms, and there are 8 corner atoms, and here in the center the metal will be present at the body center. The ligands will be approaching through these corner atoms, and there are 8 for in octahedral complexes there were 6 ligands, but in here there are 8 ligands, and in if we have to form tetrahedral complex, then we have to remove the alternate atoms present in this cube, and tell while approaching towards these corner atoms, here non-axial orbitals are present. So the energy of these non-axial orbitals will be raised. So in cubical void, the energy of dxy, dyz and dxz is raised, and the energy of dx square minus y square and dz square is under excited. So here if we found the per ligand splitting, then we like in we have to distribute this ratio as 2:3, like two orbitals are under excited and three are above upper, then these 2/5 from barycenter there is 2/5 del del in, and here it is 3/5.
Yes.
In octahedral complexes there were 6 ligands, so if we find that the del O, and if in here there are 8 ligands. In octahedral complexes there were 6 ligands, so if we find the per ligand splitting, then we can find it as del O by 6. And if we have to find this for 8 ligands, then in cubical complex, then it will be del O by 6 into 8. So it will be 8/6 del O. And if in tetrahedral complexes, the difference is that the ligands are not present at every corner atom of this lattice. The ligands are present at the alternate corners. Like if the ligand is present here, then the other ligand, after lefting this, the other ligand will be present here, and the other ligand will be present here, and the other ligand will be present here. So there are only alternate 4 corners. So in here we will find per ligand splitting by multiplying it by 4. So here we found the relation between tetrahedral and octahedral complex, that del t del t is equal to 2/3 of del O.
Yes, good. What's the difference between weak ligand and strong ligand? Why is CFT from CFT?
Sir, in weak field ligand, the weak field ligand pairing energy is high, so the pairing doesn't occur in weak field ligand because the pairing energy is high. And in a strong field ligand, the pairing energy is low, so it prefers to do pairing. And from crystal field theory point, we can say it there comes different hybridization according to CFT, because if there is a weak field ligand, it in CFT in it will split, for example, as T2G and EG orbital. Then if the ligand is weak field ligand, then it will fill first complete EG orbital, and then it will go to T2G orbital, and after that it will again fill EG orbital. But if the ligand is a strong field ligand, then it will completely fill both the orbitals of EG, and then it will fill T2G orbital. So according to this filling, there will be different hybridization in strong and weak field ligands.
Yes, good. What is pairing energy? What is the measurement of pairing energy? What is the use of pairing energy in CFT, in any ligands, complex, compound?
Serving energy is the energy which is required to pair these two electrons in this single orbital, because when we fill, if there is one electron and we are filling another electron, then there is repulsion between these two electrons. So the so to stabilize the, so there the spin of another electron is different to stabilize this two electrons in this orbital. And if the pairing energy is more, that means this complex or this orbital will not be stable if we fill both the two electrons simultaneously. And in a CFT, pairing energy plays a major role, because by knowing the pairing energy is more for or low for this complex, then then we can find that the ligand is we can find that the ligand is forming inner orbital complex or outer orbital complex.
Yes.
And also the pairing energy, we also while calculating the crystal field stabilization energy, we also write in write in strong field ligand also write pairing energy, as if there is one, if there is pairing occurring in one orbital, then we also donate it after calculating, as if we have find 1.2 dello, then we, if there is pairing occur, then we will write it as 1p or 2p according to the.
Yes. Good. What's the difference between tetrahedral complex and tetragonal distribution complex?
Tetragonal distribution complex.
Yes.
Sir, I have not about tetragonal.
What is John Taylor distortion?
Sir, in a non-linear molecule, when the there exist unsymmetry in EG orbital or T2G orbital, then it lowers its symmetry to form a stable complex. It do distortions to form a stable complex. If John Taylor distortion occurs when there is asymmetry in EG orbital and or in T2G orbital. For example, in EG orbital, if only one electron is filled, then if it is unsymmetry in EG orbital, and if three electrons are filled, then also there will be distortion occur. And in T2G orbital, if only one electron, two electron, four electron, five electron are filled, then distortions also occur uh, in EG orbital. Strong There occur strong John Taylor distortions, and from T2G orbital there occur weak John Taylor distortion. In a
Yes, good.
John Taylor distortion in
The left part. Next day we will.
CU
Yes, next day.
in
John Taylor distortion is complete part applications of CFSE. Difference between static and dynamic John Taylor distortions. Yes, no.
yes.